Again, good afternoon, everyone.
Good afternoon.
Hmm. I'm Dr. PJ Shah from SSBT Engineering College. Again, welcome you on AICT sponsored online short-term training program on digitally controlled power converters for industrial and renewable application, phase 3 under AQI scheme. And today is the day 5, uh, and tomorrow is the last day. Uh, now we're having a practical session from National Infotech Surat. I would like to welcome National Infotech team of National Infotech Surat for the practical session. Topic is implementation of PV SATCOM, and behalf of SSBT College, I again thanks National Infotech team for accepting our invitation, and we are conducting very nice session from last 3 weeks or last 15 days. My special thanks to Viral sir. Special thanks to Dr. M.A. Mullah. Special thanks to your Rajan, Junaid, and whole team for their unlimited effort to make this program success. Hmm? Uh, some announcement before starting the program. I have already shared all maximum PPTs, all PPTs till today. Also shared a YouTube link of first 3 days. Okay, and day 4, YouTube link of day 4 and day 5 is in progress. I think I will share this link also today after evening. Okay, thank you very much, all participants, for joining us. Over to Junaid sir.
Yes, sir. Thank you very much, sir, for your kind words. And it has been a pleasure to be at this STTP since, as you said, that we are conducting this STTP since October. This is the third phase of right now. So we are very much glad that you invited us, and we'll be looking forward to some much more collaboration like this in future. And we would like that if you are you want some students of you to get the most like hands-on experience, then you can also send your students or that NITech, then that would be much more interesting for them in order to
Sure,
learn this. Yeah.
sure.
Yeah.
So we're already MOU and we associate with each other from last 5 years. We will continue it. Okay.
Yes, yes, sure, sir.
Okay.
So with
You
that, we will try. We will start today's topic. So uh, before we start today's topic, we will start from where we left on yesterday. So yesterday we have yet to see the last implementation of two-stage PV inverter. So that video, small video will I will play that how we can implement the two-stage PV inverter. The first stage is the DC-DC converter, which is important for the doing the MPPT operation, and the second converter is responsible for the grid synchronization. So that we will see first, and after that when we have concluded that then we will move over to the today's topic of PV STATCOM. So I will share my screen. Okay, so I think my screen is visible. Is it visible? Arun?
Yes, it is visible, Junaid.
Yes, sir. Thank you, sir. So in this video, so audible.
Yes, it is
Okay,
audible, Junaid.
okay, thank
Okay,
you.
go. we are going to implement both of the circuit which we have previously seen, which we have individually performed. So this one is the boost converter, which is doing the MPPT, and this is our inverter connected to the grid, which we have seen the performance in the PWM rectifier. So now we are going to implement both of this converter in and getting the power from this PV panel and feeding it to the grid. So in the which way I'm trying to show you that in which way we are going to turn this whole setup on. So the first the whole thing is connected from this PV panel to this boost converter, then this link, then this is in our inverter, then there's coupling inductor, and there is a grid. So for the, first let us see the setup in setup where how they are connected. So this is our panel termination, as we have seen earlier, that this there are 6 panels which we have seen on our facility, on the rooftop of our facility. So these 3 panels we are connecting in the series, and from that there is a voltage and current sensor V3, and this is our boost converter which we have previously seen in the MPPT operation. Then there is a this is our DC link. Okay, this is a DC link. The DC link capacitor are connected here. You can see this two capacitor, and from that DC link, this is our inverter DC input. Okay, and this is our inverter AC. Okay, and this AC is connected to the grid. You can see that we are connecting the grid via this auto transformer. So the procedure for feeding the power into the grid, first we will have to maintain the 250 volt DC here in order to get the 110 volt AC at the line to line at the inverter output. So first in this whole circuit, this in the when the PV is connected to and this boost converter is connected, the whole circuit is connected. So first we are going to give this set this grid to 110 volt line to line. Then we will turn on the PWM rectifier operation, and we will maintain the 250 volt DC here. Then we will turn on the MPPT boost converter switching, so that the power coming, then the power will come from the PV, and the 250 volt is already maintained here on the DC link, and the extra power coming from the panel will be fed in the grid. So that we will see now. So this meter, this blue one is our DC link voltage. So now we have connected also one load of 200 watt, and we will give it line to line 110 volt, which is approximately 154 volt in DC. So that we are setting. You can see that. And then after we will disconnect the load, and we will turn on our PWM rectifier. So you are able to see that I set it to the 150 volt. Okay, you can, so now I'll remove the bulb. So now I'll first we will connect the web panel. So the panel we have connected, positive and negative terminal. So now we will turn on our PWM rectifier. So this DC link will be maintained 250 volt. And you can also observe the current and voltage. We will also observe the current and voltage on DSO screen. So in this condition, currently the MPPT we have not turned on yet. So you can see the voltage right now is 121 volt input voltage. The input current is 0.005 ampere, and output voltage is 246, which is also our DC link voltage. And you can see the current is not being given by our panel. So whenever I will turn on this MPPT, this current will rise. Okay, so let us turn on this MPPT. and you are able to observe that the current is increasing, and you can see you can also see from the input current that it is previously was 0.005 and now it is zero point 0.1 something, and you can see the voltage input voltage of the panel is also varying, and it is trying to get to its maximum voltage point. And you will also able to observe it on the then our DC link is also being maintained around 250 volt, and we will see that in this condition our voltage and current should be out of phase, so that we will observe on the DSO screen. The now you can also see that the MPPT is working from the this current the input current is varying. So it is trying to track the maximum power point, and you will see the current from the DC link output is 0.55 ampere something, and you can see the current and voltage waveform on the DSO screen that this voltage and current are out of phase. So we are feeding the power coming from the panel to the our grid. So this is our two-stage PV inverter setup and operation, and how we see how we are developing this two-stage PV inverter setup, and hope you understood it. Thank you.
Is there any query regarding this PV inverter setup? Two-stage PV inverter setup and development. Participants can ask the queries regarding this, and we can move further to the today's topic of PV STATCOM. I think Rajesh, sir, we can start with the today's topic, PV STATCOM. So,
Okay.
should I play that setup video?
Yeah, you play the setup video first.
Okay. Someone saying that he can only hear the voice. Is it okay that everyone is able to see the screen?
I'm able to see the screen, Junaid.
Okay. Paresh, sir, are you able to see the screen?
Yes, sir. Yes, sir.
Okay. So it might be some issue from their side. This D goes, sir. Please try to check your internet connection. Okay,
Okay.
thank
Now it is okay for sir.
you. Okay.
So in this video, we are going to demonstrate the single stage grid.
Junaid, please pause it. Okay.
Okay.
So, as Junaid has explained, so we are going to see the demonstration for PV STATCOM functionality of this inverter. So, but the previous case was the two stage. So here we are going to see the experiment setup where PV panel is directly connected on the DC link. So there will not be any boost converter. So you can see here, so PV panel is directly connected with the grid connected inverter. Then interfacing inductor and grid is connected directly. So we need a higher DC link voltage to operate or to work with this. So if DC-DC converter is there, then the lesser voltage of PV panel is also sufficient to operate or to feed power in the grid. So with this, after completion of this setup, we will see the three case studies, practical case studies. After that, again, we will come back to the demonstration where that three case studies, whatever we are going to see. With that, with support to that, how can we develop the experiment setup, similar experiment setup, uh, to provide that experiment verification if we have some new concept related to this PV STATCOM functionality or related to this application. So this is really nice concept that can that is recently in research also many people are writing many articles and many concepts they are proposing based on this. Okay, so Junaid, please continue with the experiment setup
Yes.
video. Okay.
So as we have seen in the previous cases, we have developed the two-stage PV inverter. So in the two-step stage inverter, you know that we are using this one boost converter for the MPPT purpose, and this second inverter, which is synchronized with the grid. So in this single stage operation, what happens will be that we have removed this one converter, which is boost converter, and and in this operation, the responsibility of the boost converter will be given to this inverter. So this grid, so this inverter will be doing the MPPT, as well as it will be synchronizing with the grid and feeding the power coming from the PV panel to the grid. Okay, so this is our PV panel. So this is DC link. This will be our inverter. This is a filtering inductor, and this is our grid. Okay. So in the DC link, we will have to we are setting our line to line voltage to 110 volt as the previous case. For the 110 volt, we will have to at least maintain the 250 volt DC at the DC link. So that's why we have connected this panels, which we have previously connected panels in series. So now we are connecting 6 panels in series in order to get the 220 volt near about voltage at the DC link. And so let us first see the single stage setup. So we'll see this panel PV panel first. You have already seen this panel termination. So these 6 panels we have connected in series, and this is we are getting output from the series this panel, and which we have connected to our DC link. So this is our DC link, and our DC link is connected. At the DC link, you know that there is a capacitor. This capacitor. So this is here is this capacitor, the DC link, and we have connected this load bulb load at the DC link here at the inverter DC link input. Okay. And this is the DC link of the inverter. Inverter is this, and inverter output is RYB terminals are here through this sensing circuit, and then there is this coupling inductor, and this coupling inductor then given to the our grid. Okay. So in the next video, we will see the single stage PV operation, PV inverter operation.
So I think Rajan sir, you will be continuing from here.
Okay. So this was the experiment setup. It is a similar, very similar. So where we removed the boost converter and we have connected 3 extra panel in a series with the previous setup. So we can have the higher DC link voltage compared to the two-stage configuration. So in this now I am sharing my screen where we will see the case studies related to PV STATCOM and its operation. So I think my screen is visible to everyone. Junaid, please confirm
Yes,
my
sir.
screen.
Yes, sir.
Okay. So now the first article which I found in this area was this. So where this term called PV Statcom came. So the author was Rajiv K. Verma sir. Okay. So in 2009 he published this letter, power engineering letter on the energy conversion. So he actually proposed that so whatever solar farm or wind farm connected in the large system or in the transmission line PCC, whatever large 1 megawatt, 2 megawatt power plant connected at this or 10 megawatt. So that plant can be operated as a STATCOM. Its full capacity can be utilized as a STATCOM at a night time to regulate the PCC voltage under normal condition or under the faulty condition also. And he has provided some control system as well as some results where some line to line fault or such fault are created. And in that condition also, when the solar farm or wind farm is operating as a STATCOM, at the time the PCC voltage regulates in the prescribed limit. So this was the first letter where the minimum thing with a new idea sir has proposed. So after that, many research work are uh, available in this field. So this was the first case uh, where the solar farm was can be used as a statecom in the night time. That was considered. So at the time when PV power is not available, the full capacity will utilize for delivering the reactive power and to regulate the PCC voltage under the faulty condition as well as under some loading condition, no load condition, etc. Okay. So is this clear first where the application, major application is here? So large solar farm and its capacity of whatever capacity that can be utilized at night also. So it increase considerably the utilization factor of the solar farm. So generally in the night time, this solar farm are remains idle. But if we utilize is it as a statecom, then it it its utilization is increased compared to the previous case. So this was the first case where the PV statecom was introduced in this letter. After that, in 2018, for distribution system by the same author Rajiv K. Verma and uh, Sivanasi has proposed this PV Statecom, a new smart inverter for voltage control in distribution system. So here the proposed idea was that if we try to correlate this figure, so it is suggesting the red line is a reactive power and this blue line is a active power. So during the night time, during the night time, the whatever system, so first let us see the system. So if some system is there like this, in that system at PCC it is connected. So at this side load is connected, some RLC, some load, and this is the distribution network. So because of this line inductance or impedance, so PCC voltage varies depending on the load condition. So this solar farm or solar plant is generally installed in some industry or on the distribution feeder. So there generally it is used as a just a PV power dumping. So it dumps only PV power. But in this article, it is proposed or it is suggested that so this can be utilized for as a statecom under some faulty condition or whenever the requirement of reactive power is there. So capacity of this inverter can be utilized as a statecom. So here in this diagram, it is suggested that night time, its full capacity like 10 kilowatt system is there. So full capacity can be utilized as a statecom. But when at a morning time, when some active energy is available, at that time, its reactive capability, which is utilized for PCC voltage regulation or some other reactive power requirement, that can be restricted and active power energy can be given. So here partial statecom mode it can be activated. So after the 8 or something here some disturbance is created. So in this disturbance means they have suggested that so if some disturbance is happening during the daytime when the active energy is available, then also priority can be given to the statecom for the stability of the system. For the stability of the system means here the because of some disturbance, if this grid voltage is reducing too much or increasing too much, then the active energy fed to the grid can be reduced and it can be operated as a fully statecom to support the required reactive energy to regulate the PCC voltage. So to regulate this PCC voltage. So this was the case which discussed here, and they have suggested a few operation in the control system which is very similar to the yesterday which we have discussed. So there are the two inner loop. So these two are the two inner current loop. These two are the inner current loop. One PLL is there which is extracting the grid angle. Then this is operation in the DQ reference. Then again DQ to ABC. Then some PWM operation, and that PWM operation control the switches of the, and in the outer loop ID current, ID reference is derived from the DC link loop. So as we have seen yesterday, and this DC link reference is derived from the MPPT algorithm. So whatever MPPT algorithm we are using, from that this DC reference is derived because of the single state topology. So here the DC link voltage should be regulated. DC link voltage should be regulated according to the MPPT condition or according to the solar radiation. So DC link voltage reference is derived from the MPPT technique. Then the operation comes for the reactive power. So yesterday we kept IQ star is equal to 0 in our experimentation. We kept IQ star as a 0. Here IQ star was 0. But here, so here in this article they suggested that depending on the operation requirement, depending on the operation requirement, IQ will be delivered over the ID required. So it can be delivered from this loop. So solar panel can be removed. So here provision for removing the panel is also given. So if we see here, so solar panel can be disconnected and the system is operating fully on the STATCOM mode where it control the PCC voltage according to the requirement. So this was the one of the application which was highlighted and the control was presented as a smart PV inverter control where it can regulate the PCC voltage and simultaneously it fed the PV power. So here some results we can analyze and similar result we will show in the demonstration also. So if we are using if we consider this case study, so here we can see that, so when large load is connected, so please focus in this figure. So in this figure we can see the first is a PCC voltage. In the per unit only peak value is shown per unit. Okay, here active and reactive power, and here the load condition. So when load is connected, so initially no PV operation is there, so there is no PV power, so active power is 0, reactive power is 0. After that PV is connected and the system working from this point to this point only in the active power mode. So there will not be any reactive power transfer, only active power transfer is there. So when this load is switched on, large load, at that time the grid voltage will reduce by some 20% they have shown. So per unit voltage is reduced by some 15%, it become 0.85 if we are not using it in the partial STATCOM mode or STATCOM mode. So and the stability of the system reduces because some large load is connected at PCC. So with this PV STATCOM operation, so same scenario is shown in this, but the change part is, so when load is connected at that time active power is reduced and the reactive power delivered from the inverter is increases. So that's why this PCC voltage can be regulated uh, to the defined limit. So this was some proposed idea in this article, and we can see this was a completely application oriented idea. So where the application was, some plant is there where the demand of voltage regulation is there simultaneously and it is not for large time. So they have mentioned also that the smart inverters discontinues its real power generation temporary for the few seconds like 1 minute or 30 second 40 second to regulate the some sudden change in the load. So that can be delivered by this by overcoming or by reducing the active energy generated and controlling the active energy and only operating in the reactive mode. So this was the second case study which was recently published in this 2018. In the third case study, where this article actually recently accepted, that is published by us only. So in this also similar concept we have introduced, where some this is the existing water pumping system where some 11 kV feeders are there. That voltage 11 kV voltage is reduced to zero point 0.4 sorry 0.4 kV, that is nothing but 400 volt, and it is given to the induction motor through dual starter. So what will happen? So recently many programs are going on in India where the government is encouraging the farmers to connect the PV inverter parallel to their irrigation system or parallel to their distribution system at that PCC. So what will happen if only the active energy is delivered by this inverter, then there are many issues because this is the induction motor which draws some amount of reactive power. So it also drawn from this supply. So when induction motor is operating, so our idea was that so we can connect some multifunctionality in this inverter where so when induction motor is operating at that time, so required reactive energy should be delivered from here. So whatever required by the motor, that should be delivered from here. And when motor is not operating at that time, the voltage fluctuation at this point, that should be the control, that should be control at PCC. So this was the two mode. One is a power factor control mode where it control the power factor. So when it control the power factor when irrigation is required, so water irrigation is required or water pumping is required. So when water pumping is not required at that time, so if daytime is there, then active energy is feeding in the grid. Because of this active energy fed, there is chance that PCC voltage fluctuates. So that fluctuation might be in range of some 50 volt. So that can be regulated by delivering some supportive reactive energy from this inverter. So this was the whole idea, and similar control system we have presented where the PLL we have used second order generalized integrator for estimating the reactive power required by the motor and the PCC voltage regulation. So here the IQ will be derived from, if we want to operate in the power factor control, then IQ will be derived from the load current, required reactive power, and otherwise it will be derived from the PCC voltage control. So here, so in the experiment result, if we see, so this was the experiment setup we have developed to observe the change in the voltage at PCC. So PCC voltage was varied by connecting the parallel load or by injecting the active power. And the weak grid at the laboratory is created by connecting some inductor, 6 millihenry inductor in series with the grid. So here the voltage variation we can observe under the loading condition. So so two mode, one is a power factor control mode. So if we see the power factor control mode, so this was the power factor control mode, results for power factor control mode. So this is without the PF control. So first figure is without PF control, where induction motor draws some reactive power, and when we turn on the UPF operation, so our inverter will deliver some reactive energy, and the current drawn from the mains reduces, and the Vs and Is become in phase. If some active energy is increasing from the PV side, so under the UPF operation, now the current become out of phase. Now you see it is very small amount, so it is very small amount of current. So here it was in phase, now it become out of phase. Out of phase means our PV inverter is delivering the more energy required by the motor, greater than the required by the motor. And here we can see the energy delivered by the PV inverter is quite higher than the required by the induction motor connected directly with the motor. So the PV energy is quite higher than this, such that this whatever excess energy is there, it is delivered to the grid. So this was the one of the application of the PV STATCOM where the reactive energy is utilized to maintain the UPF operation at a PCC. Now the second operation where the motoring operation is not required, so motor is not having any demand for generation of the reactive energy, then the full capacity can be utilized for mitigation of the grid voltage fluctuation. So first case is without voltage control. If the variation in the parallel load is happening, so this is the is current is changing because of parallel load connected at PCC. So IQC component is zero. We are not delivering any reactive component from the inverter. In that condition, whenever load is switched on, at that time the grid voltage is reducing and increasing depending on the load condition. So steady state voltage variation can be observed. But in the similar case, whenever load is switched on and off, at that time if we turn on the voltage control loop, so at that time this fluctuation can be minimized and voltage PCC voltage can be regulated simultaneously to the some active power delivery. So this ICQ or IQC, that is nothing but the reactive energy delivered from the our uh, PV inverter that regulate the grid voltage. So similar case will happen when parallel load is not disturbing, but when you inject some active energy in the grid, at that time also because of that line inductance or the line impedance, the variation in the PCC voltage can be observed because of the weak grid condition. In particularly in at the farm place where the long transmission line are used to deliver the, sorry, not long but short transmission line, but it is having a large distance, so it can it is corresponding to the voltage variation. So voltage variation can be observed on the PCC. So this voltage variation can be observed even if the PV power is changing. So under the PV power variation, so this was the PV power variation under the some cloudy condition. At that time, the voltage was fluctuating, but if we turn on the reactive power operation or voltage control operation, then it can be minimized. So this was the some experimentation or some three case studies I have presented. So one for the irrigation system, water irrigation system, which is currently in the installed in our farm place. So this where we can connect in parallel some multifunctional PV inverter, which give the advantage of the active energy as well as some the power quality issue can be handled using this in that practical condition. One is this was the third. Second one is then for the distribution system where the full capacity can be utilized as a STATCOM to overcome the some instant loading or some fractional of time if some loading is high. Because of that, some variation in the PCC voltage can be controlled. So this all case study is application dependent. So here also application, different application, here also some different application, here also some different application. So same concept is utilized to for the three different application. One is for transmission, one is for distribution, and third one is at the load end. So at the load side, we can, how can we utilize the capacity of PV inverter to solve the power quality issue present in that particular application. So I hope this PV Statcom idea is clear with these three case studies. So where the only part now we will see is the control of power factor control or the voltage control that we can achieve using this. So and the other thing is the PNO algorithm will give the required DC reference which regulate the active power delivered from the from the PV source to grid. So from the PV to grid, whatever active power is delivered, that can be regulated using this variation in the DC link voltage. So Junaid, I think I'm done with this case study. Is there any doubt related to this three case studies? Any question from the audience side? Then we will go for the experimentation of the similar setup where the PV Statcom algorithm we will demonstrate, or its result we will demonstrate by operating it. Is this clear? These three case studies? Is this case three case studies clear to everyone? Hello? Hello? Am I audible, Junaid?
Hello. Yes, sir. You're
Yes.
audible.
Okay, so I think this with these three, I am clear. I delivered what I wanted to deliver. That in the PV Statcom there is no major difference, but we will control the reactive energy according to our application. But the how to implement this, that an implemented setup that you demonstrate, please. So in first demonstration, you start. Okay, thank you. So here in this, we are going to see only PV active power energy, how we are transferring in the grid. So there will not be any reactive energy transfer, only active energy transfer. So only PV inverter operation with a single stage setup. Okay, continue, Junaid.
So in this video, we are going to see the operation of PV inverter single stage operation. So we have already seen the arrangement of our hardware. So for same as the two-stage inverter, how we have powered up that inverter. So the similar step we are going to imply here. So first I am going to give you the 110 volt AC line to line, which will be resulted in the DC 150 160 volt. You observe. So now it is set to 160 volt. Okay. So as you can see that this is right now the solar panel is not connected here. You can see that this is the negative terminal of our solar panel and the positive terminal is not yet connected. That we will connect after seeing the DSO. So you can see the yellow is your voltage and blue is the current. So you can see that this current is taking from the load is taking from the grid. So whenever I connect this panel, that current will become zero, which will imply that the current from the grid is zero. So now this bulb is running on our solar power. So now we will disconnect this our load, the DC load. So now we will maintain 250 volt DC as we have already done in the two stage. So now I will just turn on this inverter by pressing this key. So first let us also understand the LCD screen. So this 250 volt DC, this is our reference voltage. As you know that in the single stage, to maintain the DC link voltage, the voltage reference is given by the MPPT. So this is that voltage reference given by the MPPT, and this is your actual voltage. Okay, and this is your ID reference, and this is your actual ID. This is your this is your IQ reference. This is your actual ID, and this is your actual ID. So this is your voltage reference. Then this is your actual voltage. This is your ID reference. This is your IQ reference. This is actual ID, and this is your actual IQ. Okay. So now I will turn on our inverter, and it will try to maintain 250 volt the DC link. Okay. So you are able to observe that 250 volt DC is being maintained. So in this mode, right now we are not implementing any MPPT technique. Rather than we are giving the voltage reference manually by setting this port here. You can see that by varying this, I will be able to observe the voltage reference in the LCD screen being changed. So now I will change the voltage reference. Then accordingly the power will be the actual voltage will change. Okay, so this is your DC link voltage is trying to maintain at 239 volt. Okay. and it is changing. Okay. So right now I change it's set up to 20 volt. So the actual reference voltage and the actual voltage is matching, and you can able to observe that your current being taken from the panel is 0.7 ampere DC, and with that we will also verify by the our DSO that your voltage and current are out of phase, and that will suggest, that will indicate that you are dumping the power from the panel to the grid. And in this case, in that case, your ID reference will be negative. So you can see that on the first row that the last quantity is my ID reference. So it is coming minus 1.1 something. It is constantly changing. So the power from the panel is changing. That's why it is constantly changing. Okay. So your actual ID is also changing, and now. So this is how the PV inverter and the manual MPPT tracking we are doing right now. So you can see the current right now has increased, that the condition, weather condition has increased. Again, it is some low condition, in low irradiation. So the current here, voltage current, the grid current is also changing accordingly. Okay. So this is how the PV inverter single stage in a manual MPPT we have tracked. So in the next video we will also see the how the actual MPPT will give the voltage reference, and it will try to track the MPPT point. Thank you.
Okay, so in this video, what we have demonstrated is, so we have not implemented the uh, MPPT algorithm, but the whatever DC link reference is to be regulated, that we was giving from some variac which is connected at ADC. So what it's do is it varies continuously according to our requirement. So output is not change depending on the MPPT algorithm for the peak power condition, but we was operating our system on the different point of that PV curve, com consider by considering the current irradiation. So we can change the PV voltage manually by changing the reference. Now in the next video, what we will see is where we will remove the whatever potentiometer we have connected, and the reference DC link voltage will be derived from MPPT algorithm, which is the PNO we have implemented here. So now you can verify it that now the MPPT voltage or DC link voltage varies depending on the irradiation available, and it continuously maintains the peak power. So it will not operate in any non-MPP point. In the transient, it will operate for a while, but after that it will reach to the required MPPT condition. So DC link voltage will be regulated automatically using that MPPT algorithm. Please play, Junaid, that video.
Yes.
So we have already seen the PV inverter single stage operation, but in that operation we have seen that the MPPT which we are doing manually, we are using this code to vary our voltage reference of the DC link. So now that we have changed. MPPT algorithm, what have been observed algorithm, will be giving us a voltage reference. So you already know that this LCD display, this first quantity is voltage reference. This is second is your actual VDC. This is ID reference. This is IQ reference. This one is your actual ID, and this is your actual IQ. So by pressing this PD7 button, you will be able to observe that this is changed to 240 volts, which is being, this voltage reference is now being given by the MPPT algorithm per turn observed. So, so now, so first we will start on our method. So I am setting it to PD7, which is 250 volt. So initially we will set it to 250, and then we will switch it over to the MPPT PN algorithm. So again, with the same scheme, we will first now we will set our line at 110 volt. So you will to observe this 165 volt DC, and again the same way we have connected this load, the DC that we will discuss. So now I first connect this our panel, and you will see the current this panel is taking from the sorry, this bulb is taking from the panel. So now I will connect the panel, and you will see the current will become zero. So that means that your load is taking the current from the directly from the panel. Okay. So now I will remove our load. So now I'll again turn on the inverter. So now this 240 volt, 244 volt will set to 250 volt. So our VDC, this is also our VDC. So it is set to 240, 250 volt. Okay. So now we will change our this voltage reference, which is given by our manual port, which we move on to the MPPT algorithm. So now I press the down button, and you will see this voltage reference is now being given by the our MPPT algorithm. You can see that our control technique to match this actual voltage and reference. You can see the on the screen. The voltage reference 240, the vector voltage is trying to maintain this voltage reference. And you will also observe that the current you are taking from the panel. And also the voltage and current is out of phase. So we are feeding the power into the grid from the panels. So again, let us see the LCD screen. Your voltage reference is 240, and your actual voltage is also trying to maintain that to 240. So this is how our MPPT will work in this PV inverter single stage mode. So hope you get the insight and the details of the PV inverter, and we will see the PV STATCOM mode in the next videos. Thank you.
Junaid, now we'll take one break and then we'll continue. What do you say?
Okay, sir. Yes, sir.
Okay.
This is okay. We will continue at 340, right?
Okay. 340.
Yeah, 340 will continue, and we will conclude today's session.
So we'll have one break and we'll come back at 340. Okay. Thank you, Junaid. Thank you.
340, huh?
340 will continue.
340. Okay, thank you.
340. Okay. Okay. PV inverter, where we have implemented two-stage PV inverter. So it is very similar. So now if we want to implement this, whatever demonstration you have seen, so the same method we are following for the verification. So once if we are programming it, then the verification is the most important thing. So how to verify that is it working correctly or not? So that verification part. So what we are doing is, in the first case video which we have already played, in that what we did is whatever reference value of the voltage, this at outer DC link loop, that was varied by some variac from the outside of the controller. Some variac is there. Using that, it is varied, and this value will corresponding to the some non MPPT operation as well as the MPPT condition. So if this is the PV curve for the particular condition. So if we vary this V, if we vary this V, this is the single stage topology. So if we vary the P, V, so if we keep V at this point, so power injected in the grid will be maximum. So our grid current, if this is the voltage, and if second is a grid current, so grid current will be some maximum value. So if we vary if we vary this point VDC voltage greater than some peak value, so let's assume that 250 is a peak value, so 250 corresponding to 250 some peak power is coming. So if we vary this reference, our power at this side as well as this side, so for 270 as well as for 220, it will reduce the current, so current will reduce by some magnitude. If we are going further this side, then the current reduce further and it will become zero. If this is reduced more than some value. So we can get this point or we can achieve this point by implementing the MPPT algorithm. So that MPPT algorithm, how we can do is, so that MPPT algorithm in the previous program only we are observing. So first experiment what we did is the same control system without MPPT algorithm we have uh, shown without MPPT algorithm. So but we are controlling the PV power by adjusting the PV voltage, by adjusting this reference voltage. Reference voltage means DC link voltage. So DC link voltage is directly connected with the PV. So that DC link voltage is nothing but a PV voltage. So we are controlling the PV voltage using the PV inverter. So this voltage in the second case what we have shown where the only PV power is allowed. So Q was 0, still STATCOM mode was not demonstrated. Q was 0. So what we was doing is, so was this reference voltage was derived from the MPPT algorithm. So that was the seventh part in the implementation that we have shown you yesterday. So here instead of D, MPPT algorithm will give the reference DC-link voltage required to give or required to extract the maximum power from the MPPT. So only the change part is, so if we see the change part in the program compared to the two-stage topology and single-stage topology, here instead of DPV, algorithm will the output the reference voltage. Output will give the reference voltage. And second thing is we don't have the DC-DC converter, so we don't need to generate the PWM pulse for the boost converter. So this two part will remove and the algorithm giving the reference DC. So this is the only change will happen in the program. So now the part by part, if we divide this program part by part, so first already we have seen how to verify it. So first we can verify in the PWM operation. So that we have done already. Second is we can verify the program that is it tracking the peak power or not by operating it in the non-MPPT and MPPT condition. So we were operated this algorithm at different point by adjusting the reference DC link voltage. Different point. So depending on this reference point, the active power delivered to the grid is reduced. Now we came to know that it is working correctly, control is working correctly, inner loop and outer loop. Then we have connected the MPPT loop. That is nothing but PNO control. So now PNO control will continuously maintain the DC link voltage reference to this point. So always the peak energy will be delivered to the grid. Peak energy will be delivered from the PV panel. So now this step is not there. This was the previous. This step is not. So active energy, whatever generated, it will be dumped inside the capacitor if we are connecting capacitor, and by regulation of the capacitor, it will be dumped in the grid. So this was the case uh, where the active energy transfer with this loop. So only change with the program file is this is removed. It's our duty cycle control or boost converter control is removed. Other things are same. So it is not a major change we can say. So control can use the control from that. So now the next video we are going to see the only STATCOM operation. Only STATCOM operation where what we do, we will disconnect the PV pack. We will disconnect the PV. The capacitor is connected. This capacitor is connected. Capacitor is connected here. This is capacitor. So what will happen? No active energy transfer from grid to PV side or PV to grid side. So there will not be any transfer of active energy. So this will not be. Only the reactive energy transfers. Only the reactive energy transfer here. Only the reactive energy transfers or exchanges between this according to requirement at PCC. So at PCC we have connected some RL load as well as some RC load also we have connected RC. That will change the power factor at PCC. So we are measuring the current at here, source current IS. We are measuring one source current here. We are measuring the load current here IL, and we are measuring the inverter current, that is nothing but compensator. So what we are doing is this IS and the VPCC should be always in phase the STATCOM operation. Should be always in the STATCOM operation. Or here what we are doing is first we are giving some manual input here. So if we see this, so IQ star was 0 in previous case. So now we will change this IQ star in the range of -3 to +3. So when -3 is there, then it acts as a inductive, and when +3 is there, it acts as a capacitive. So depending on this plus or minus IQ, then it will change the reactive power delivered from the inverter. So that demonstration we are going to see now in the next video, where the system will operate as a some STATCOM function, but in open loop. So we are just testing the reactive power capability of the inverter in the experimentation. So how to do the experiment with reactive energy. So it is we can say that the demonstration of STATCOM also. So I request Junaid to continue and share his screen for demonstration of that STATCOM operation. Please, Junaid.
Yes, sir.
Hello, sir. Please check your voice. I think some participants are not receiving your voice.
No, sir. Actually, that comment was during that break.
अच्छा,
Before
और
the
I can see.
ओके 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 ठीक
So
है
at the time, no one was speaking. Thank you,
ओके
sir.
ओके ओके
Thank you, sir.
So I'm playing the previous STATCOM operation videos. Okay, sir.
Okay.
So in this video, we are going to see the demonstration of the PV STATCOM working in only STATCOM mode. So at the night time when yeah, the solar power is not available, so what is the use of your this inverter? So then at that time this inverter will be working as a STATCOM mode. So for that, we'll see that performance of this inverter in the STATCOM mode. So now let us check the LCD on the controller that this first on the first line you see this 250 is our reference voltage. This second quantity is our actual VDC. This is our VD command, and in the second line which is IQ reference and which is currently -1.4. This is ID and this is actual IQ. So in the STATCOM mode, we all know that STATCOM compensates the load current by providing its capacitive or inductive current. So in the leading or lagging form. So this IQ reference represents that current should be lagging or leading. That IQ is calculated by the according to your load connection, but here we have not connected any load right now. But in the actual STATCOM mode, in the actual grid, what happens that your three-phase load and the three-phase load current is sensed and that current is converted in that IQ and IQ component are decoupled, and then that IQ reference negative of that IQ reference is being given to in order to compensate compensate. So now we will see. Now we are manually changing this IQ reference. So now with this PD3 button, we will change the magnitude of it. So it will change. So first, let me show you that it is being changed. So now it is 1.4, and then it is changed to 2.8. And again I will press it. Then it will become 1.4. And if I press this PD4 button, so it will become the plus 1.4. Okay, and you can see that it will also change in the magnitude of 2.8. Okay, so this way we will see the performance if this in leading and lagging mode. So now I will give it 110 volt line to line voltages. So we have connected this bulb load on the DC link in order to just maintain the DC link voltage, so that the capacitor voltage is in her hand. So after that we will disconnect this load. So now I am disconnecting this load. So now I'll just simply turn on our inverter. So with this button, I will turn on our inverter switching. So you are observing that your DC link is maintained to 250 volt, and we will see the current and voltage waveform on the waveform on our DSO screen. So you can also see. Okay, so let us see on the DSO screen. But right now our reference was 1.4, my negative 1.4. So it means that your current is in a lagging mode. So you can observe that the yellow is a voltage and the blue is current. So your current is lagging from the voltage. Okay. So if I press the PD4 but PD3 button, as I shown earlier on the microcontroller, your magnitude will be changing. So your 1.4 is changed to 2.8. So you can able to observe that your current. I have pressed it. That you are observing that your magnitude of this blue current is increasing. Okay. So I think it is visible to everyone. So now we will also see now I'll again decrease it to 1.4. Okay. So you are able to see that the magnitude is changing. Okay. So it is settled now. And now I will change it the minus 1.4 to plus 1.4. So the current will become leading. So now I press this PD4 button, and you will observe the current being leading from the lagging. It is taking a little time because of the soft start and soft stop mechanism, and you can see that your current is now becoming leading. Okay. Now I will increase the magnitude of this current. So 1.4 to 2.8 I will change. So you are also able to observe the magnitude being increased in the DSO screen, and it is also in the leading. So this is how your inverter will be working in a PV STATCOM mode. and hope you at the night time it will be working as a STATCOM mode and doing the compensating uh, of your system. Okay. Hope you understand this STATCOM mode operation in the PV STATCOM. Thank you.
Okay, thank you, Junaid.
Yes,
So
sir.
here, actually, we have observed the only state operation where our active energy. So if I share my screen again, okay. So it is shared. So now if we see here in this diagram, so our third case study. So now what we experimented right now is we have controlled this IC magnitude, and we have verified that our reactive power capability in the inverter. So we have experimented the reactive power component for its positive and negative value. That is nothing but leading and lagging reactive capability of the inverter. So now the task will come is, so now we can verify with a PV and Q both simultaneous. So whenever PV energy is transferring, at that time the voltage at PCC and current both will be out of phase like this. This is the voltage and the current will be out of phase. Current will be out of phase like this. It will be out of phase like this. But when only PV is available or only PV is activated, so whenever reactive is also activated, at the time some uh, phase shift can be observed at this compensator side. So there are the 3 point we are having of the current. One is a load current, one is a load current, one is a compensated currents, and one is a source current. So our target here can be anything depending on the application. So in this particular application, if induction motor is drawing too much reactive power or some reactive power, hence the some power factor is poor at grid side. So with parallel to this active energy transfer, we can supply some reactive energy from here at a local point. So at PCC, unity power factor can be maintained. It is uh, uh, well-known technique, and it is STATCOM operation. Generally, only the if PV is not available, then the only reactive power is supported. So we need to sense the reactive power energy available at load end. So we need some sensors. So here only one sensor is used in this particular article, where the reactive energy required for this is derived from the single current sensor. So and the whatever IQ component that is derived uh, parallel to active energy transfer, it will be delivered from here, and the uh, UPF operation we can achieve. So same, if we want, if our target is the only grid voltage control, then this current sensor is also not required. So irrespective of the requirement of the reactive power from the load end, we can we can regulate the grid voltage, PCC voltage, by regulating the reactive energy delivered by the inverter. So now the next time in the next video, or that is I think the final video, where we will see the both operations simultaneously, where some amount of active energy is also delivering to the grid. Parallel to that, some amount of reactive energy also delivered or transferred to the grid, or it can be exchanged. It is exchanging with the grid. It might be the leading or lagging depending on our application. So this totally the application dependent. So wherever we are connecting, so depending on that we will choose the this reactive power operation. So I request Junaid again to share his screen and play that video. Okay, last video. Okay, Junaid.
Rajan sir,
Hello.
one question here.
Yes. Yes.
So the
Hello.
thing that hello,
Yes. Yes, sir. I'm listening you.
okay. The concept that you have explained just now,
Yes.
by which we can implement the low voltage right through capability.
Yes, yes, why not, sir? Let me share my screen again and there we will see. Okay, again. So is it visible now, sir? Is it visible? My screen?
No, sir.
Hello?
Yes, yes, visible. Yes, visible.
Yes, yes, visible. So the second case study, what I have shared with you, that is for LVRT condition only. That is for LVRT condition. If you see the abstract of that article, the low voltage right through performance of the PV STATCOM is demonstrated through both PSCAD as well as experimental demonstration. So in the second case study was there, inside that the same low voltage right through, whenever low voltage condition is there, at that time, so whatever system is available or it is connected, that full capacity of this inverter can be utilized as a STATCOM. It deliver the full reactive power and the zero active energy. So here also in this figure, if I zoom this figure, you will be more clear. So here it is acting as a partial STATCOM, but when some voltage problem is creating, at that time it operates as a fully STATCOM. In the same condition I have shown in during the results also. So in this article some results are given. So in that results also, so you can see that whenever this loading is applied, at that time the PCC voltage is not changed. Why? Because the active power delivery is reduced and reactive power delivery is increased. So your system is acting, or it is acting as a full STATCOM. So under the LVRT condition, it enhance the stability of the system. So is it clear, sir? Hello?
Yes, sir.
Okay, okay. Any other query related to this? So I have said this three case study. So in this all three, the application is a different. Control system is same. So it is totally depend on the application oriented control of Q or reactive energy has been done, but P control is the same. So P is whatever P energy is coming that we are delivering, but in the second case study the P is also reduced if the higher priority is there. Wherever voltage is the major priority, then we will stop the active energy and we will utilize the full VSC capacity for reactive compensation or the voltage control, PCC voltage control. Okay, thank you. So can
Sir,
we
what will be
move
the
forward?
sir? What will be the sir? I have one more question.
Yes, yes, yes. Welcome, sir. Please.
Uh, For the LVRT capability, what will be the minimum capacity of this PV system which we are connecting to the grid?
That is the right question. So you will find many articles. So it depend on the PCC condition. At PCC, how many loads are connected. So that you need to do the separate study that at what value of VSC we can utilize to avoid the possible LVRT condition. So first we should know the what is the possible LVRT condition. So we can do by some simulation study in PSCAD or in even in the similar software where we can connect the same network, and with that network what is the maximum possibility of reducing the voltage and how much time it is taking to reduce that. Depending on that you can connect or you can choose the VSC or the whatever inverter connected with you. If we are keeping it blindly, then there is a possibility that it can cover up to its maximum capacity. So it depend on the both one, the condition required at fault condition or at PCC, and the rating of the VSC. So rating of the VSC depend on the analysis. So we need to do the correct analysis that at end of the what is the LVRT condition or maximum voltage it can reduce, so that we should be clear and how much in that condition, how much energy we are able to deliver, how much reactive power we are able to deliver. So these two are the major thing or challenging thing. So for particular case, finding the LVRT condition and according to that how it can avoid this using this, that we should calculate. It is the calculative thing, sir. Okay, so you might find some reference in this article also. So you can download this article and you can visit it. PV Statcom, a smart control for voltage control in distribution system. Okay, sir.
Oh, okay, sir. Okay, sir.
Okay, okay, okay. Any other questions? We can have the questions till we have time. So only one video where we will demonstrate both. So here actually we are not showing you some LVRT fault or its protection, or just we are showing the demonstration where we have implemented this inverter. We have implemented this inverter, and this inverter is capable to solve this. So what condition is, so if some LVRT is happening, so LVRT condition we need to formulate. So in particular third case, I have created a weak grid. So how we have created in the laboratory environment. So in the laboratory environment, you see, please carefully here. So in the laboratory environment, we have connected 6 million inductor in series with our grid. So what will happen because of this impedance drop, whenever some current passing through this circuit or some load is increasing or decreasing, at that time PCC voltage varies. It will vary. So if I connect this load bank, then PCC voltage will vary. If I inject some active energy from here, then also PCC voltage varies. So depending on this condition, some voltage variation I can observe. So that voltage variation was in the range of this. So in the result also I have highlighted. So this was in range of 113 and 140. So RMS voltage was varying from 110 to 140. So after successfully implementation of our control, so under the same change, that voltage was regulating to 130 volt. So our PCC voltage was regulating even in the reduced voltage condition. So similar condition you need to create in the laboratory environment, and you should know that with that condition how much voltage it is reducing, or the worst condition whatever you are able to achieve. And for that you can design this system. For rating of the VSC we can design. Okay sir, is this clear now?
Yes, sir.
Hello. Okay, thank you. So can we move forward, sir? If you are clear, we
Yes.
will move forward.
Yes, sir.
Okay, thank you. Junaid, please continue with the video demonstration. Okay.
Yes, sir.
So in this video, we are going to see the working of the same arrangement of the single stage PV inverter, and we will see it's working in the PV STATCOM mode. So you can observe that all the hardware arrangement is same, from the solar panel to voltage sensor to our DC link and our inverter, then our DC link capacitor and our grid. You can see, or you can observe all the arrangement are same. But now we are going to observe that this PV inverter is also working in a STATCOM mode, so which will justify our PV STATCOM title of this configuration. Okay, so again, you all know the steps how we are going to power up this. So first I will set the DC link voltage, which will be around, which will result in the 110 volt line to line AC voltage. Then I will connect the panel, and you will observe the current of the current will become 0. That load will take current from the panel. You can see I have connected the panel here. Okay. So now I will disconnect this load. So again I will turn on this inverter by pressing this switch. And as we have seen in the previous case, that your IQ, in this PV STATCOM mode, you know that the IQ reference we are changing. So also first let us see the LCD screen, that you all know that this is our VDC reference. This is our actual VD. This is ID reference. This is IQ reference. This is actual ID, and this is actual IQ. So in this case, we will see this IQ reference will change. So you know that in IQ reference we calculate according to our load conditions. So it will give the leading or lagging component based on the load. So now, as we have seen in the previous video, that this button will result in the reference of the IQ. You can see the IQ reference is changing to 0 to minus 2.8, and it's 0, and the leading and lagging will be changed by this button. Okay, so now I will first turn on the inverter in the IQ reference as a 0. Then we will change it to the magnitude, and also we will change its leading and lagging position. So first let me start this inverter with this switch. So you can see this we are dumping the power into the grid. So right now you can see the current and voltage and current is changed. Okay, so now I will give the IQ reference as a minus 2.8, minus 2.8. So your current will become lagging. Okay, so I have set this minus 2.8, and you can observe on the DSO screen that the current is now lagging. Okay, so now when I will again decrease this minus 2.8 0, then IQ reference, and again it will be in phase. So you can see the gradual change. Okay, so now it is in phase. So now we will see it in the lagging mode. So now I will press this button and it will become in leading mode. So this minus sign will be positive. You can see this is 0. Now I will change its magnitude to 2.8. So you will be observing the its operation on the DSO screen, that the current will become leading from your voltage. So you can see that it is now leading. Okay, and you can also verify on the your LCD screen of the microcontroller that your IQ reference is minus 2.8 and your actual IQ is also coming around 2.8. Okay, so this is how our PV inverter works in STATCOM mode. And so this is, I think this justifies our PV STATCOM. Let us again see, bring it back to IQ reference, bring it back to the 0, and we will see that your current will come again in phase. Out of phase of the voltage. Okay, so now it is coming out of phase, and so this is how our PV STATCOM works. Hope you understood this PV STATCOM operation. Thank you.
Hello, am I audible, Junaid? Hello.
Yes, sir, you're
Hello.
audible. Yes.
Okay. So with this, actually, we can conclude this. But there are some practical implementation. Of our experience. I want to share that. So if someone want to implement it, So first divide in the part. So first is we have forwarded in the practical sessions. So first step by step you verify whatever if you are using this space or RTLab or this whatever controller we have used using this Visum block set. Then first you verify the all the blocks separately. So like ADC, PWM block. So if I highlight, so this is the ADC block. Is it working properly or not? That we should verify first. Then PWM operation we should verify. Then key operation for start stop whatever we are using, that you should verify first. So part by part, first you verify the whatever peripherals. After that you verify your grid angle estimation if you are implementing it, so it is working properly or not. By stopping everything, just apply grid voltage and angle estimation. So whatever method we are following, that is it working properly or not. After that the DQ transformation we can implement. So without turning on, we can verify the VD, VQ, ID, IQ, is it working properly. After that, we can move forward to the implementation of this. So here, no shortcut. So here we need to implement all three loops simultaneously, and its tuning also required to do the simultaneously. So, but what we found from our experience is it is not as difficult as we are feeling while in the simulation. So if we know the right method to put the value, so within one or two try we can reach to the solution. We cannot say that it is optimized value, but it works good for the particular condition. So this is also possible, but step by step one should move forward and implement this. Okay, so this was some comment from my side. If you this now stage we will open for the question answer. If anyone has any difficulty or they want to discuss their case, or their if what they want to implement in this renewable thing using this controller or some other, then they can share their experience or they can ask any query if they are having related to whatever delivered or whatever we have explained here. Please, participant, you can ask some question or if you have some query.
Sir, I have few questions.
Wait a second, sir. I am actually not getting your sound. Yeah, now it is okay. Please speak.
Sir, while simulation, actually I'm
Yes.
working on the DC microgrid, and while simulation, actually I just started working on this microgrid, DC microgrid. So
Okay, sir.
during simulation, sir, the selection of L and C value is very difficult. I found very difficult
Okay.
because I have calculated through some formula which is given in the literatures, but
Okay.
I found sometime the value of L or C which I have calculated through formula is working properly, but sometime it is not giving the right answers for the
So
simulation.
LNC means whatever filter we are using, interface filter. This one. Is this, sir?
Yes, sir. Not for the
Okay. So
actually I'm talking about the boost and buck boost converter, which is
okay,
connected to the
boost
primary
and
and
buck
the
boost
PV.
converter. Okay. So that actually we didn't face any difficulty in there, but
Okay.
that might be possible that maybe whatever value you are considering, or sometime what is happening in when we are simulating at that time, also the PV panel whichever we are choosing, if that is
Mhm.
correct or not, how can we verify? So whatever PV panel you are considering or you are modeling, is it working for throughout the range? So we face sometimes the problem that if we are reducing the irradiation, solar radiation below 500, then it is not working, whatever converter, but it should work. So then we found that there was some problem in our implementation of our PV panel in the simulation, particularly in the simulation using that four equation when we are modeling. So we are modeling at some different equation or different way, then it is working. So in without panel if we check, then for the same power level converter was working. But when we connect the PV panel or whatever model we have used, so you might check in the model side that it might be your converter is working correctly, but your PV model is not correct, or it has some limitation in that region, whatever irradiation region, you are not getting proper output. So that also you can verify. Other thing is sampling time. So here sampling time of the simulation, whatever you are choosing, that is also important thing. So you are using MATLAB, sir?
Yes, sir. I'm
Hello.
using MATLAB, sir.
Okay.
Yes, sir.
Okay. So
MATLAB.
their sampling time selection is a very critical thing that we found when we have started implementing it. So now we are becoming very precise that what should be the sampling time of each block. So you can see different color you are seeing here. So this color
Yes, sir.
shows the sampling time of that block. So we are choosing the sampling time also such that it follows the it give the correct answer. So there also we are arranging some special STTP on the selection of sampling time and the different simulation of different circuit. So where we will do the hands-on on the simulation, and where we will show that. So if we are not choosing properly the sampling time of the each block or particular block, then your simulation fails. Though your concept is correct, your calculations are correct, but because of the selection of the sampling time, it fails. So that is also the possibilities you can verify in that whatever you are simulating, sir. Okay. So generally we
So
are
my
using in the
second thought
variable
is
step.
okay, okay.
Generally you are working in the variable step size simulation, but right now in this all the simulation as well as the experimentation, we are using fixed step. So each calculation we are controlling its sampling time. So that is one thing that you should verify, that how to
Sir,
simulate in fixed step.
in Opalati also we need a fixed step.
Fixed step set, right? Correct, sir, correct. In every digital implementation a fixed step is required. So what we are doing is, generally our approach is that we will make a simulation too perfect. If we are getting some problem in the experimentation, same problem we are getting in the simulation also. So it is very one to one to the experimentation. So if I am facing some problem in experimentation, same condition if I create in the simulation, then I can get easily that where is a problem. So generally through simulation, sometime we are solving some problem of hardware also. But besides that sampling time is required. Okay. So that one point we want to comment here. It is difficult to
Sir, in
explain
PV
here.
for the PV simulation, is it recommended to
Yes.
use the ready-made PV block which is available in the simulation, or we need to have the what we call the modeling of PV through equations
Okay.
that will work?
Okay. It depends, sir. It depends. Actually, we was working on the 2014. So this whole thing we have done in the 2014. So there the PV model itself it was available. It is not available. So after I think 2016 version or higher version, it is available. So even I have not checked that model is working correctly or not. But whatever model we have using there, it is having some problem. So you can re-verify. You can verify that model for by considering the different cases. If it is not failing in that conditions, means if we know the concept, it should work like this. If it is not working, means there is some limitation. So that you should verify first. So first verify your simulating model with by considering different scenario. Okay, sir.
Okay, sir.
Okay. Any other queries or something? Okay. So thank you everyone. Thank you for your everyone. Thank you everyone for active participation, as well as I want to thank SSBT organizers, Paresh sir and team, for allowing us to deliver our this practical sessions. So I am really thankful to sir. Okay, Junaid, over to you.
Yes, sir. Thank you very much, Rajan sir. And with that, we are concluding our this third phase of the STTP, and we are very much thankful to SSBT College and Paresh sir and Thakre sir and the team for inviting us for to conduct this STTP on such an interesting and trending topic of renewable energy. So we are glad that we can deliver what we have experienced in our laboratories, and it was such a pleasure for us. And we would like that some this kind of activities will also happen in the future too. So thank you very
Sure,
much.
sir. Sure, sure.
Thank you everyone. Thank you for
Sure,
every
sure.
participant.
Mm, yes, sir. Uh, thank you very much, National Infotech team, for delivering a wonderful last 15 days. Three sessions you are delivered very nicely. I'm very much thanks to Team National Infotech Surat for their unconditional effort You have presented nicely 15 sessions from last 3 months, 5 session in each, 5 days in each session. It will definitely help all faculty members, all participants, and research scholars. Actually, as you know, we have MOU with National Infotech from last 5 years, and we have organized various training programs for UG and PG students, as well as many faculty development programs were also organized, and definitely we got the we got to benefit from this different training programs. My special thanks to Dr. M.A. Mullah, who is a mentor of National Infotech Surat, Director Mr. Viral sir, Mr. Junaid, and Mr. Rajan, and whole team. You have accepted our invitation and you have delivered a wonderful practical session. It is really, really very helpful for students, participants, and faculty members. You shown the very latest technology, softwares, and many things. Really, you added many knowledges with us. Okay, and thank you very much, all the participants. You have attended this program patiently. Uh, Thanks once again, National Infotech team. Definitely, we will organize good programs in futures also. So this is actually we have received a grant from AICT for 3 programs, and we have completed three programs successfully. Okay, thanks once again. Some announcement. Tomorrow is the valedictory function. Guest of tomorrow's sessions is a Dr. A.K. Panchal. Is also from SUNIT Surat. He will talk about the fundamentals and application of solar systems. And this program will be conduct around up to 11:45, 12:45, and from 12:45 we will start the valedictory function. And in valedictory function, it is the oral feedback. You have to give the oral feedback. Please give your name. So if you are interested, please tell your name. I am writing the name. Anybody interested in oral feedback, please give your name. Anyone, please? I have received 1 or 2 names from my WhatsApp. Shall I write the name? Anyone? So you can speak on feedback program. Anyone? I request Chauhan sir, Dr. N.D. Chauhan sir, Nandokishore sir. Shall I write your name? Chauhan sir, Nandakishore Chauhan sir, Sham sir, please.
Sir, no,
Yes.
sir.
अच्छा. Chauhan sir, Mahesh sir. Yes.
Yes, sir.
Okay. Thank you, Mahesh sir. Sonal madam, Yugal is always ready. I wrote your name, Yugal. I think I'm writing the name of Dr. N.D. Chauhan also. Chauhan sir. Okay.
Yes, sir. Please write my name, sir. No issue.
Huh?
Yes, sir. Please write my name. No issue.
Yugal sir, na?
Yes, sir.
Yes. Yugal sir. Yes. Okay. Our program will start at 12:45, and it will be for 30 minutes or 40 minutes, and after that our test will start. Okay. If you have any query regarding whole program, whole 5 days, please ask me. If you have any query, I think all the materials I have shared, all videos also I have shared, 3-day videos I have shared. Now at evening I will share the remaining videos also. I think up to tomorrow all things will be shared. All material also shared.
Sir, phase 2 video is not shared yet. Phase 2,
It's day 4 and day 5 is remaining.
yes, sir.
Up to day 3 is already shared. Day 4 and day 4 and day 5 is in progress. Okay.
Sir, I'm
So I
talking
think
about phase two, sir. Phase two
phase two
program,
is
sir.
also there, is also pending works. So
Yes,
we'll
sir.
share definitely. Don't worry. So due to the lot of video, it takes too much time. That's why
Yes,
I will share.
understand, sir.
Phase one is already shared. Three we are sharing. Two we will share later. Within 5 days we will share the phase two also. Hmm? Okay. Thank you once again, everyone. Please join the sessions. Please tomorrow you join the session. Okay. Thank you once again. Okay. See you tomorrow. Please join at 10:45. Junaid sir, once again, thank you.
Yes, sir. No problem, sir. It's our pleasure.
Okay. Please, National Infotech have also shared the link. Please fill up this link. Okay.